Welcome to Matcom. In this particular video, we will be discussing one important aspect from NCERT Chemistry Class Plus 2 in the chapter Haloalkanes and Haloarenes. This particular aspect is very important. This particular aspect can be asked as a 3-mark question or a 4-mark question separately in the examination. You can see that in many years they have asked this particular question in the board examination. So before going into detail, going to the video, I would really like to inform you that there are various playlists are available in our channel. Please check those particular videos. Please share with your friends, with your teachers, family members and all. Please help us. As a token of gratitude, please like to this particular video, share with your friends, subscribe to our channel. So it would be extremely helpful or extremely encouraging towards us if you subscribe or share to our videos or channel. Okay. So the question is, aryl halides are extremely less reactive towards nucleophilic substitution reaction. So when you're considering an aromatic halides, why they are less reactive towards nucleophilic substitution reactions? So there are many reasons. The first reason is called the resonance effect. First reason is called the resonance effect. What is the resonance effect? Why it is happening now? So when you're considering a halogen is attached to a benzene ring, a halogen is attached to a benzene ring. This particular electron pairs in halogen can undergo conjugation with the pi electron cloud of the benzene. So the bond can be, the lone pair of can be shifted and can form a double bond between carbon and halogen. In order to maintain the valency, this particular bond will be shifted to this particular carbon. So as a result, so you will be getting a partial double bond between the carbon and the halogen. The lone pair of electron in the halogen is utilized for the partial double bond formation or the double bond formation. The halogen will be getting a partial positive charge. As a shift of this particular bonded electron towards this particular carbon, carbon will get a negative charge. The next step, this particular bond can form, or this particular negative charge can form a bond between these two carbon. As a result of it, this bond will get shifted and a negative charge will be accumulated in this particular carbon. So the next resonating structure will be like this. Double bond between carbon and halogen. Halogen will be having a positive charge. A bond will be generated between these two carbon. Already existing bond, a negative charge will be generated. In the next step, this negative charge can form a bond between these two carbon. This bond can be get shifted and form a negative charge over here. So what will you get? So you will be getting next step, this bond can be, negative charge can be shifted and a bond will be generated between these two carbon. As in order to maintain the valency, this particular bond will get shifted towards the halogen. As a result of this, the aromaticity of the benzene ring will get re-established. So this particular halogen will be having the lone pair of electrons. So during resonance, you can understand that there is a partial double bond character. Partial double bond character is generated. Partial double bond character is generated between the carbon and the halogen. Carbon and the halogen. If a nucleophile has to substitute the halogen, mean the bond between the carbon and the halogen has to break. But a partial partial double bond character is generated between the carbon and the halogen. It would be very difficult to break the bond between carbon and halogen. I repeat. Since due to resonance, a partial double bond character is generated between carbon and the halogen. In order to substitute a nucleophile, we need to break the bond between carbon and the halogen. Okay. So since a partial double bond character is generated between carbon and halogen, it is very difficult to break the bond between the carbon and the halogen. That is why the haloarenes are less reactive towards the nucleophilic substitution reaction. The first reason. The second reason is the difference in hybridization. Second reason is difference in hybridization. When you're considering a haloarenes, the halogen is attached to a carbon which is sp2 hybridized. This carbon is sp2 hybridized because a double bond is established, sp2 hybridized. When you're considering a haloalkanes, the halogen is attached to a carbon which is sp3 hybridized. When you consider the sp2 hybridized carbon, its percentage of S character is 1s and 2p, that is equal to 1 by 3 into 100, that is equal to 33.3%. When you consider the S character here, that is going to be 1 by 4 into 100, that is equal to 25%. That means in the case of an sp2 hybridized carbon, the percentage of S character is more. When the percentage of S character is more, S orbital is an orbital which is more closer to the nucleus. So when it is more closer to the nucleus means, what will happen? The shared pair of electrons will be bonded very closely, or this bond will be more stronger. Why? This carbon is sp2 hybridized. sp2 hybridized orbitals are more closer to the nucleus. So the bond will become more stronger, or that shared pair of electron will become more closer. As a result of it, bond strength increases, bond length increases. Bond strength increases, bond length decreases. Bond strength increases, bond length decreases. When bond length decreases means in order to break that bond will become more difficult, or if the bond strength is more, it is very difficult to break that particular bond. So the difference in hybridization between the carbon halogen bonds, or the difference in hybridization of the carbon in haloalkanes and haloarenes. Then another thing is that during resonance, we came to understand that the negative charge density is generated in the benzene ring, especially at the ortho and para position. So due to resonance, since more electron charge density is generated at the ortho or para position as a whole in the benzene ring, it will be very difficult for a nucleophile to come and interact on this particular aromatic ring system. That is the third point. And the fourth point is that assume that whenever you are having a haloarenes, if the X minus is cleaved means it will be generating a positive charge on the benzene ring. This is nothing but called a phenyl carbocation or phenyl cation. When it possible, when it is following an SN1 mechanism, substitution nucleophilic by unimolecular, when a carbocation is generated. We know that the positive charge on a benzene ring is highly unstable because the positive charge is generated on sp2 hybridized carbon. That makes the system highly unstable. So the possibility of SN1 mechanism is completely ruled out due to the instability of phenyl carbocation. So what can we say? Due to four reasons. The first ring, that due to resonance, a partial double bond character is generated between carbon and the halogen. Second thing, as a result, the negative charge density is generated in the benzene ring, especially at the ortho and para position. Due to difference in hybridization of the carbon in haloalkanes and haloarenes. The fourth point is the instability of the phenyl carbocation. Due to these four reasons, this particular haloarenes do not favor nucleophilic substitution reaction in normal condition, but in very extreme condition it will favor. We will see that particular thing in another video. Hope the explanation is very clear. If you need any clarification, do let me know in the comment section. As a token of gratitude, please like to this particular video, share with your friends, subscribe to our channel. Keep watching, keep learning. Thanks for watching. Bye.